I would like to welcome you all to what is our second Willis Lamb lecture. He may not need an introduction, but perhaps it's worth mentioning that Willis Lamb, who was Wykeham professor at Oxford from 1957 to 1962. Prior to that, his career lived in the United States. He was a student of Robert Oppenheimer's. Then he went back to the US after his stint at Oxford. He's most famous for his work on the Lamb shift, for which he won the Nobel Prize in 1955. He was a remarkable man. He was a theorist by training who realized at some stage that the spectrum of hydrogen was something, if it was known really well, would allow quantum electrodynamics to make progress. So he taught himself enough experimental physics and collected enough collaborative help to actually carry out the experiment himself. There's actually a beautiful book by Sylvan Schweber, which I highly recommend. It's called QED and the Men Who Made It. And in it, there's a long description of Lamb's heroics in bringing this off. So along with the measurement of the anomalous magnetic moment of the electron, these were the two precise measurements, and then set up the challenge for quantum electrodynamics, which was met by Feynman, Schwinger, and Tomonaga, and Dyson for their Nobel in QED. So we began this lecture series last year in Lamb's honor. Our first lecturer last year was Mahadevan from Harvard. I hope some of you had a chance to hear him last year. This year, we are delighted to have Professor Herman Verlinde from Princeton, where he is the class of 1909 professor, and just stepped down actually as chair of the physics department, so he's particularly feeling energized on the research front. I was there for much of his chairmanship, and I can remember him looking a lot less relaxed during much of it. Herman's career is in some ways coterminous, not that the second terminal is in sight yet, with the field that's known as string theory. He began his PhD fairly close to 1984, which was this year of this paper by Schwartz and Green on anomaly cancellation and superstring theory. And he was then, along with his brother Eric, a student, I think, at Utrecht. And so they began to work in that area, both of them. And so Herman did his thesis under the supervision of Gerard 't Hooft, I'm sure you all know of. And then after that, I think he went to Princeton as a young man, then stayed till he was an assistant professor, and then went back to Holland. And then in 1999, he came back to Princeton. Actually, both he and Eric came back. Eric eventually escaped to go back to Holland, but Herman stayed, much to the delight of the rest of us who were there. So during this period, string theory, has been a program with various phases, various superstring revolutions, initially perturbative string theory, then various dualities, ADS-CFT, and most recently, the influx of a lot of ideas from quantum information theory, and also considerations normally associated with statistical mechanics, such as questions of chaos and ergodicity. And at each of these stages, Herman has been right in the thick of it. So in fact, he's a great person with a perspective on this field from its infancy to tell us about where the program stands and where the most recent developments leave us at this moment. And fortunately for us, that's exactly what he has chosen to do for his Lamb lecture. So with that, Herman.
Okay, thank you, Shivaji, for the kind introduction. Maybe as a small little tidbit of information, Shivaji, when he arrived at Princeton, he took my office when I went back to Amsterdam, so I had to move to another office when I came back to Princeton. And that's it. So it's an honor and a pleasure to be here and to give this lecture. What I'll do in this next hour, maybe you know what, I'm going to make the screen a little bit more visible, which I'm told is done by one of these buttons here. I think this works. Good, a bit better, right? So in this next hour, I'm going to sort of talk about things that I've been thinking about over time, but I'll talk about it sort of from a historical perspective. Indeed, it's great to be in a place like Oxford, where indeed also the history of physics has been sort of very sort of influential in many of the developments that I'll talk about. But indeed, even to understand the questions that we're thinking about right now, understanding sort of where those questions were first posed and when they were first posed is actually very useful. So I'm going to get started. Indeed, there are going to be a lot of things that I'll sort of cover. So it's a bird's eye view of a lot of questions, indeed having to do with quantum mechanics and space-time. Many of these questions have been around, and we have found answers. But I think the appropriate place to start, in my mind, is actually basically almost 125 years ago in a paper that was written by Planck. So when I was learning physics, at some point I heard about Planck units, and they, at the time, actually to me, sounded sort of futuristic. So I was actually struck by the fact that Planck, indeed himself, in a little one-page appendix to a paper he wrote actually before he made his famous discoveries, that he actually had noted that there were natural constants in nature that if you sort of combine them would give you a natural set of units. We have the meters per second and the gram, and also for temperature, there are units. And Planck already, and this is not discovering a new law of physics, but nonetheless, I view this as an enormously deep insight that he took essentially the correct units to call the natural units. Indeed, whenever I do calculations, I'm indeed working in these Planck units where the speed of light is set equal to 1. Newton's constant is set equal to 1, and the Planck's constant, which we now call the Planck's constant. By the way, the numbers here are all different. C is still C. F is now called h bar, which is the Planck constant. There's another constant, which is the Boltzmann constant, K, which actually has a different name for, but in those days, it was actually called the Planck constant. But he put them all equal to 1, and then when you do that, you get certain units for length, weight or mass or energy, actually, in some ways, and time. And those units are actually quite strange because, again, the length unit is 10 to the minus 33 centimeters. We call it the Planck length. The Planck mass is 10 to the minus 5 gram. That's a grain of salt. The Planck time is enormously short, 10 to the minus 33 seconds. The Planck temperature is enormously hot. Nonetheless, if you know you're German, then he's talking here about basically that if you would communicate with someone in another planet, and you could even say perhaps in another universe, what are the units? You're not going to talk about seconds or meters. You have to start using natural units. And in a certain way, what Planck did at the time, he kind of foresaw a set of revolutions that were going to happen in physics. Because he kind of realized that these constants were all fundamental. And indeed, at the time, 1899, it was actually a time where people thought that physics was almost done, that we basically knew everything. And if you hear other people say that at this current time, we actually know everything in physics, that everything we're doing is just sort of filling in the details, just think about back to that time. And we were thinking about important questions back then, and we're still thinking about the same important questions right now, or different ones, but still equally important. But the key point that I want to make is that those 4 units that Planck introduced indeed point to fundamental rules of at least structures in physics that we're still trying to understand better and how they are connected. And the reason I call them fundamental is precisely because they are universal. Space-time, we believe, is a universal property of, obviously, the world around us. Gravity is something very fundamental. Quantum mechanics, actually, Planck himself introduced that later, which is h bar. And indeed, thermodynamics is an important component of the whole story as well. In the first two, space-time and gravity, namely speed of light and Newton's constant, he basically partially foresaw that there's going to be a revolution pretty soon after that. And Einstein, indeed, he was very much motivated by work by Planck, but also just by thinking about indeed the rules of electromagnetism to indeed introduce a special theory of relativity, which I'll talk about briefly later. Of course, the most famous formula in physics is one of them, one of the equations that came out of that. And then 10 years later, by thinking hard about sort of more generally how gravity should work in this same framework, he developed the theory of general relativity, which is now how we understand the dynamics of space and time and of gravity. So that sort of came after Planck's paper, and indeed it already was an era in time in physics where suddenly everything was being sort of turned upside down in terms of the way we were understanding things. And indeed, Einstein, his main point about special relativity is that he took rules that we kind of knew in electromagnetism, and he kind of turned around the logic, which forced us to start thinking differently about space and time. So, of course, let's go to the next ingredient, which is, let's see if this thing works. There's always this chance that it happens to me, that when I have things that have buttons, things go wrong. Okay, here we go. I went too far. Let's go back. Here we go. So quantum mechanics. So quantum mechanics indeed was sort of discovered in the next sort of 20 years, starting indeed with Planck, Bohr, Einstein, Heisenberg, Schrödinger, Dirac. So many people sort of made discoveries, but indeed it revolutionized the way we were thinking about sort of how atoms work, how we describe in particles, and how we are thinking about even the predictions in nature. And then over the next 2 decades, 3 decades, quantum field theory was developed as a way of incorporating special relativity. And up to this day, I would say that quantum field theory is still one of the most successful frameworks in which we're describing particles and the physics. And indeed, currently, again, we're still doing experiments in the CERN particle collider. And all the experiments that we're basically doing there can be described to high accuracy and not up to the accuracy that we sort of can test perfectly well with quantum field theory. And that's the framework that people developed, and essentially sort of the current state, and this you could say is sort of the almost finished state of the current understanding of how nature works in our universe, is that at the shortest distances, we're looking at indeed particles that can be described in terms of fields. There's names, and for every particle, there's a certain field. And indeed, as I was had on the previous slide, quantum field theory can describe particles, but also forces, and it can describe the strong and the weak and the electromagnetic interactions. And if you combine them all together in the standard model, that's precisely what's being tested at LHC, and it works extremely well at the shortest distances and the highest energies that we have available. Now, the same laws of physics should apply sort of in other questions as well. And when we go to all the way the longest distance scales, then we're talking about cosmology. And then Einstein's theory, which here's the Einstein equation, will basically describe what happens at cosmological scales. It describes what happens at gravitational scales, provided indeed also that we have the right sort of parameters that we put into our models. Then basically we can describe things all the way from the biggest structures in the universe, the Big Bang, to the shortest distances that we have. So you could wonder, okay, if this all works so well, and essentially right now again we're testing it on many levels. What are the questions really that tell us that there's still something deeper going on? So the questions that indeed one can ask, for example, okay, there's dark energy. So if we look indeed at the energy in our universe, it's only since, so let's say, almost 30 years that we actually know that there's a thing called dark energy. And we actually still don't really know what it's made up from. It's actually sitting here, this number lambda, that's the dark energy. But as you'll see later in the talk, actually dark energy is probably not just a single thing. It might be actually something that's made out of many more constituents than we maybe realize. And if you look at the constituents in our universe, the things that we actually can give names, like atoms and photons, is only a small subset of the things that are actually there. Indeed, there's dark matter. We don't know what it is. And dark energy is indeed one of those mysteries. Now, there are other questions. I talked about the largest scales. Again, in the last 25 years, we've learned an enormous amount of how cosmology works. If indeed we currently look at the sky, we see the Big Bang in a certain way directly. Indeed, there was the moment where sort of the photons were kind of released from the Big Bang. We can see that moment, and people have done enormously accurate measurements of seeing the cosmic microwave background of radiation that comes from the hot plasma that was basically present during the Big Bang. And people have done enormously precise measurements of the fluctuations. And part of the idea is that these fluctuations indeed they need have sort of lead to differences in density in the early universe, and that those density fluctuations actually were the seed of all the formation of structure in our universe afterwards. And it's still a very open question of what generated actually these fluctuations when we started, when the universe started. Now, you may have heard at least what the prevalent theory is of how these fluctuations come about. And remarkably, the theory that people have sort of developed for this is one where the initial fluctuations in our universe were actually quantum fluctuations of something that we don't know yet exactly what it was. Maybe it was some sort of internal clock that our universe had, or a thing that was called the inflaton. And indeed, when you have the theory of inflation, which indeed postulates the presence of that clock, it's really, again, the quantum mechanics of that clock that leads to these fluctuations. And I'll be honest, again, I'm a theoretical physicist, and I can look at equations, and I can believe what people have done in terms of calculations. But as a person, I'm at least certainly amazed that, first of all, we have the courage of saying that things that we discovered at the shortest distance scales, like quantum mechanics, can describe the structures that we're seeing at the largest distance scales. But currently, that's our best theory that we have. But it's still one of those places where there are questions. And let me mention another question that comes up, if again, my pointer works the right way. There we go. Is that I showed you the fluctuations, but those fluctuations, if you actually look at the actual fluctuation, these are fluctuations in the temperature of order 10 to the minus 5 Kelvin. The actual background, microwave background, is 2.7 Kelvin, and the fluctuations are exceedingly small. And what that means is that if we look at that point in the sky, or if we look at that point in the sky, the temperature over there is exactly the same as the temperature over there. And when I say the sky, I'm actually talking about something that's like 15 billion light years away from us in that direction, or maybe around roughly that. And the question is, how is it possible that if we go all the way that far away in that distance and that far away in that distance, how is it possible that those things look the same? And that's called the horizon problem, because basically the point is the following: is that okay, well, maybe there was a way in which all of those things were coming from the same structure, because this is how we know, people, at least the fluctuations over there, know that they have to do the same thing as over there. But according to the Big Bang theory, there wasn't essentially enough time for things over there to be correlated with things over there. So we have to do something a bit more dramatic, and that theory is called inflation. And I'll talk a little bit about that later, which indeed will partially explain this question, but it also will raise new questions by itself. So these are already two examples of questions that have to do with the largest structures. And as you'll see, actually, indeed, in my talk, is that the questions that we're going to be asking about sort of how we understand nature, indeed have something to do more with things happening sort of at larger scales. these are big objects I'm going to be talking about. I'm going to talk about the universe. I'm going to talk about black holes. And there are questions that we have about those structures that indeed we don't know the answer to yet. And we'll see where that's going to lead. So indeed, as the next sort of ingredient, indeed, thermodynamics or information is going to play an important role in the story. Last century, we understood many things about how things work with energy, with collisions, and sort of, we think about the material structure of our universe. Whereas sort of in the current times, we're talking very much about information. Again, we're living basically in the information age. And indeed, one of the key questions that people are asking is also, hey, there's this quantity called entropy, which is basically a measure of information. And where is it hiding in the universe? And indeed, if you look, there's a lot of information in the universe. Information means, okay, where are all the atoms? Where are all the particles? And indeed, photons, neutrinos, dark matter even has a lot of information content. But maybe slightly surprisingly, the part of our universe that kind of has the largest amount of information in it are the black holes. And actually, there's even more information later on that will come, which has to do with dark energy. So precisely the things that we don't fully understand, like black holes and dark energy, when it comes to information, will indeed sort of create the largest, if you call the elephant in the room. And with black holes, one of the things that will sort of show up is that the information that is in a black hole is actually not something that you can immediately see, because again, the black hole is just black. But it will show up as a quantity associated with the black hole when we start thinking about something that's called quantum information. So indeed, after this introduction of what are the bigger questions, let's indeed start talking a little bit more about what underlies sort of the rules by which we're thinking about these things. So indeed, in quantum mechanics, again, I already talked about what happens, again, if you think about atoms. But in the last, I would say, 20 years or so, people have started to think about quantum mechanics in a different way, where indeed we're not just talking about objects like sort of atoms, but we're trying to manipulate quantum information where we can start controlling it in the same way as that we're controlling indeed a computation on our laptop, where we want to know that if we ask it to do a certain thing, that we actually know what comes out. And the same thing as what sort of the fundamental unit of information in your laptop. In quantum mechanics, that turns into something that's called a qubit. And most of you are aware that in quantum mechanics, the difference is that you can have information that's not just in a given state where a bit is only 0 or 1. The key feature of quantum mechanics is what's called superposition, of course, where we can have the sum of the two with some coefficients that will determine the probability of finding either a 0 or 1 when we do a measurement. And famously, for quantum mechanics, you can have both at the same time. And the thing is that when you have that possibility, then the next thing you can do is you can start not thinking about only single qubits. You can put them in a pair, or you can have many of them. And then it's basically the property of entanglement, namely that you can have different states of the different qubits in your system that are correlated in a way that actually indeed is encoded in the state, even if the particles are not at the same point. They can be correlated. And that quantity, which is called entanglement, at least in English, in German, it has in every language actually has its own name for entanglement. But at least that's the quintessential quantum mechanical property that distinguishes quantum mechanics from classical physics. And it's also the quintessential property that people try to leverage these days when they're building sort of bigger quantum devices in which they try to basically manipulate quantum information. So that's sort of the one of the engines basically of the current developments, where indeed the fact that we're building these days quantum devices that not only manipulate, say, 1 qubit. Up to now, we can go, at least the recent numbers are of the order of 10,000 qubits, or maybe 1,000. But we're basically trying to crank up the number of bits that we can control. And if you're a computer scientist, then perhaps you would not be impressed if you can manipulate 10,000 bits, because again, the number of bits that are controlled by my watch is like the trillions or even more. But the fact that in quantum mechanics you have this thing called superposition actually means that you can do certain computations way more efficiently. One way of thinking about it is that in a quantum computer, you can, if you're asking a question, you don't need to ask one question at a given time. You can ask many questions at a given time. Another way of thinking about why quantum computers are so good at solving problems is that, right, for example, if you want to find a needle in a haystack, it's actually pretty hard to do. And in many cases, a quantum computer might also have a hard time of doing it. But it turns out that there's many questions that are hard for a classical computer that are more akin to asking to find a periodic array of needles in a haystack. And then it turns out that quantum computers are actually particularly good at doing that. And this was indeed something that Charles Bennett, who's one of the people that developed sort of all kinds of new ways of thinking about quantum mechanics and quantum information. That's how he characterized sort of the power of a quantum computer. And indeed, the fact that there is such a thing as the Shor algorithm that can factorize large prime numbers, which more efficiently using a quantum computer, is one of the reasons why we are currently kind of indeed in a period where literally indeed people are building these devices. At Google, and you can have a sort of quantum chip where you're building all these systems of qubits that can interact with each other. And it sort of also realizes the dream that Feynman had sort of expressed in the early 80s, where he said, hey, if we want to understand sort of the miracle of quantum mechanics, maybe there are useful things that we can do, but also actually quantum devices or things that we can actually make in the lab, maybe the best way for ourselves to actually understand quantum mechanics itself. So indeed, we're exploring sort of a new direction where quantum mechanics has its manifestation, indeed, at the largest sort of, where the frontier, where we're talking about, is more the frontier of either, say, complexity or ways of doing, new ways of doing computation, where we need manipulating the quantumness sort of at its largest scale. Although not quite as large scales as I was talking about earlier, at least with the Big Bang. But nonetheless, at least we're seeing that quantum mechanics doesn't have sort of literal limitations. So here I'm going to go from indeed quantum to space-time on the next slide, because quantum information is sort of by itself indeed a big field, and it's currently sort of certainly growing. But indeed, there's an interesting interaction between questions that we've been thinking about in connection to space-time and the developments that are happening currently in thinking about quantum computers. And indeed, it turns out that things like quantum error correction and entanglement indeed play an important role in how we think about space-time. So the next few slides, I'll start talking about space and time, and indeed quickly we'll get to questions that indeed will connect with this notion of entanglement and other things that show up in quantum mechanics. So let's start at the basics, at least Minkowski spacetime. Indeed, the fact that we have Lorentz invariance currently, again, it seems like a given, although it actually, as you'll see, it will create some tension precisely when we start thinking about quantum in connection to spacetime. Being at Oxford, I do also want to show, at least, of course, in the next few slides, I'll do the same thing, a representation of spacetime that's called the Penrose diagram. This is Minkowski space over here, where this is sort of moving to the right, say, and this is moving to the light left with the speed of light. Vertical is time, horizontal is space. Penrose, and he's very conveniently sort of decided that he wanted to think about the global structure of space-time, and then he brought infinity back in at a finite distance just by essentially some transformation. And then constant locations in space become these curved lines, and infinite distances now become finite distances in this diagram. So I'm going to show later on a few diagrams like this in the context of where we start talking about black holes. And the main thing I want you just to remember is that information on this diagram, and it can only travel as fast as the speed of light at most. And that's the key property that we want to sort of keep an eye on. And as you'll see, actually, at some point, we're going to get ourselves into trouble by assuming, like Einstein did, that moving faster than the speed of light is not possible. But nonetheless, Einstein had a strong argument, because indeed, if you've gone through logic yourself, if you would be able to go faster than the speed of light, you would be able to do strange things like going back in time. And everyone has seen movies where these things happen. So the key thing, as I said, that I want to sort of test is the assumption that there is such a thing as sort of a practical way of representing how information travels in space and time. And as I mentioned, we can nowadays do these computations. And what this diagram here represents, and I had an earlier diagram like that, which was rotated by 90 degrees. Basically, what this thing represents is the following. So here I have a bunch of bits, and I can start applying gates to it, where I change the value of those bits. And I keep doing that at every next moment in time. And then if these bits sort of are communicating with each other, you can easily see that changing a bit over here will indeed lead to effectively something that looks like a light cone, where this information actually will have spread out over a large number of bits. And basically, so I'm going to see how this picture of how quantum evolution through a computation can be mapped to how we're thinking about space and time. And the thing that's going to bring us into trouble are black holes. And black holes, of course, again, they were already discovered, at least as a mathematical solution to the Einstein equation, by Schwarzschild. Actually, his paper already appeared before Einstein had published his paper. And Schwarzschild found this solution that we now call a black hole. And only in the last 10 years, we kind of know from various observations that these black holes really exist. We had some good guesses that they are there in the universe, based on sort of indirect measurements of X-ray binaries and all that. But now we have an image from the Event Horizon black hole, the Event Horizon telescope. And that black hole, basically, the fact that we're looking at it like this is light coming sort of from the surrounding. It basically proves that there are things that are bending the light enormously, and that the amount of mass that's in this small region, the only explanation that we have for it is that that should be a black hole. And of course, again, most of you know again what a black hole is. Again, it's a part of space-time where light cannot escape. There's a thing called the horizon, and one of the tools of reasoning that we are using in my field is to come to grips with the fact that there is such a thing as a horizon. Now, a priori, you might think a horizon is not a big deal, and one way of thinking about it is precisely that if you think about our horizon, nothing is happening at the horizon. You go to the horizon, you can go through it. In some ways, the same thing has happened true for a horizon in a black hole. For a black hole, one way of thinking about it is that, in some sense, to stay at one location in a black hole, you kind of have to, or at least in the black hole space-time, you kind of have to work upstream. You have to sort of work against the gravitational field. And it so happens that there is indeed this location where you basically have to go faster than the speed of light if you want to escape from the black hole. It's not true that the black hole sucks up everything around it, because it actually, in some sense, it's just an object with a certain mass. You can go into an orbit around it. You can do all kinds of things sort of when you're close to it. But once you pass the horizon, then basically you get sucked up. Another thing, of course, how we now know that there are black holes is indeed because of the gravitational wave observations, where we know that there are binary systems of black holes that merge. So the fact that they exist by now is sort of something that we kind of have tested in many ways. But of course, we still have to do measurements in order to verify that Einstein's theory of relativity indeed describes these equations. When we see a black hole, it always rotates. So this is actually why I have Kerr over here. It took people 50 years, at least. It's quite remarkable. Schwarzschild sort of found his equation in like a few months. And again, Peierls sort of found the solution for the rotating black hole 50 years later. And basically, his equations indeed accurately describe our observations, both of the rotating black holes, sorry, of the binary black holes, and of the supermassive black holes at our own galaxy, and the bigger galaxy that sort of gave the first image of a black hole. So if I look at this merger actually of black holes, as a theorist, I'm actually seeing something different. I'm seeing basically two systems, and a black hole to me indeed is actually made out of stuff. And I can think about it essentially the same way as we can think about, say, the nucleus of an atom, or indeed a very complicated atom itself. Except that the black hole has many more degrees of freedom. It looks from the outside like a black hole. Nonetheless, basically it has dynamics. You can see it has sort of, it's doing something. And clearly the black hole that was created by the merger is bigger than the black hole that was there initially. And from the point of view of sort of understanding what a black hole is made out of, this is a situation where we initially have something that we call out of equilibrium. And then, of course, when the black hole is just, again, one of these objects that just looks like a black hole, at that point, it's in equilibrium. It looks completely smooth. Now, normally, if you have a system and you bring it out of equilibrium, there's a certain amount of time it takes to reach equilibrium. And what's completely remarkable, if you think about how big these black holes are, and this is, of course, a simulation, but this is also something you can measure through the gravitational waves, and basically within less than half a second, a black hole reaches equilibrium. And if you think about a system that can reach equilibrium that quickly, it needs to be something that can scramble, or at least that can basically equilibrate information enormously quickly. So, so let's think a little bit more still about space and time, because again, that's going to sort of get us confused at some point. So here's a simple diagram of sort of a collapsing star, which is indicated by green. So this is sort of matter that falls, say, as a spherical shell. So every point of this diagram is a sphere, and then light sort of goes inwards. Actually, this trajectory is the spherical shell that forms the star. Sorry, that forms the black hole. And then at the origin of the black hole, you have a thing we call the singularity. Most of the interesting physics actually happens at the horizon. And the horizon is basically the place that if you want to escape from it, you essentially have to go with the speed of light. It will still take you a little bit of time, and then eventually you can escape. If you're over here and you try to go away from the black hole as quickly as the speed of light, you're still not going to succeed. Basically, your future lies within this region, and you're going to fall on the black hole singularity. So this is a space-time diagram that I'll show again later. There's another diagram, which is more the Penrose diagram. And the Penrose diagram, again, I showed you the one for Minkowski space, which basically was this little square. And then it turns out that there's a region which actually is light-like, because if you want to sit at the horizon, you have to move at the speed of light, which we call the horizon. And this thing sort of makes a little bit more clear what makes a black hole a black hole. It means that you can actually go through the horizon. And in the previous slide, it should have been clear that going through the horizon is something you can actually do. But then by the time that you're here, your future, and it points upwards always, you have to reach the singularity. So this is the Penrose diagram of a black hole. And again, causality basically forbids you from escaping from it. Now, there are all kinds of funny things that will now start happening. Up to now, I think I've told you most of the things that basically we've almost sort of know from standard physics. There are a few things that sort of become less standard. It turns out that if you do the mathematical equations of general relativity, if you look closely, you can actually find that there is a nice space-time that you can consider, where the black hole is not part of our universe by itself. It turns out that basically you can extend the whole solution to another site. And then this would be what we would call a parallel universe. And it indeed turns out that if you fall into the black hole, it's not that you can go to a parallel universe, although again, movies have told you that you can. Because indeed, if you fall in, you cannot go faster than the speed of light, and you can reach the singularity. Nonetheless, there's a certain way in which this space-time indeed has a structure here that connects the two sides. And this is our universe, say. This is some other universe, and there's a bridge between them. And Einstein, with some collaborators, Einstein and Rosen, they already also noticed that there is this sort of connecting region. They call it at least we could now call it the Einstein-Rosen bridge. Or actually, Einstein, of course, was also at Princeton. Another colleague, at least physicist that spent many years also at Princeton and thinking about black holes and actually naming them. John Wheeler, indeed in 1968, he indeed sort of had also a very sort of good sense of how to give things names. When he thought about black holes, he said, well, black holes have no, he gave them the name black holes. And then he also said, well, they have no hair because they have to be parameterized only by their mass and by their angular momentum. And for the rest, they can have charge, and that's it. There's nothing else you can sort of assign as a property of a black hole. Again, he also had another thing that he gave a name, wormhole, which was basically this connection between the two universes. This is a drawing that he made, and it's hanging in a hallway in Princeton of a black hole. Oh, sorry, of a wormhole. And again, he had many sort of ideas about this, and he indeed understood that relativity, general relativity, would become an important field. And he had many people around him at the time that started thinking about indeed how to design the gravitational wave detectors, how to think about information and black holes. And one of those people was one of his students, Bekenstein. And he said, well, hey, if I take a black hole and I break, say, a cup, which means that I'm increasing the entropy of the cup, because if you break something, you increase the entropy. But now I want to hide my sort of the evidence of my crime by throwing it into a black hole. And at that point, the black hole basically will just return to this equilibrium state where you cannot see what I've done. So how can that be consistent with the second law of thermodynamics, that entropy and information basically, first of all, the information is preserved and that entropy increases. So Bekenstein started thinking about this, and he indeed came with the conclusion that black holes actually have entropy. Not long after that, actually it was Hawking who did his calculation, where he actually was much more precise about sort of the pre-constants, and indeed he derived that if something has entropy, it should have also a temperature. And actually quite remarkably, so his paper is now 50 years old, almost to the day. So it was March 1st, 1974, that his paper came out in Nature, which he called black hole explosions. Sounds a little bit sort of tantalizing, but indeed he was basically pointing out, and he had done this calculation that there is a temperature, and then he already thought about the idea that there might be black holes out there in the universe that have very small masses, and that indeed this temperature might actually have led them to sort of become very small over time, and that the temperature would be large. That's why he called it explosions. And indeed, this kappa here is called the surface gravity. It turns out to be 1 over the mass of the black hole. And for any of the black holes that we have in our universe, the temperature that Hawking computed is not particularly large. It's something like 10 to the minus 5 Kelvin or something like that for a solar mass, a couple of solar mass black hole. Which is smaller than the microwave background. Nonetheless, we are theorists, and indeed one of the things that we're imagining is that we could make a black hole sort of in empty space, and then the fact that it has a temperature actually means that stuff can really escape from the black hole. Again, that's a surprise, and quantum mechanics or quantum field theory basically tells you that this could happen. And in quantum field theory, you have this famous notion of sort of a virtual pair, where indeed there are fluctuations where basically you temporarily create a particle and an antiparticle. You can think about it sort of as an EPR pair. One of them goes into the black hole, and the other one escapes. Combined, they have zero energy, but essentially this thing kind of extracts energy from the black hole. So that was his calculation. And basically at the time you can think, hey, was this the correct calculation? But this result is 50 years old, and it really has become essentially the Rosetta Stone. It's really sort of the kind of result that tells us that there are many things going on, that there are particularly deep things going on with black holes that essentially will force us to indeed sort of complete, in some sense, the program that Planck was foreseeing. Because indeed, if you take the fact that black holes have a temperature, and you apply the second law of thermodynamics, namely that a change in the system always comes with a change in entropy, which is related to the change in energy. And indeed, black holes also have an entropy. Here I wrote down the formula indeed with all the constants in there, and Hawking indeed himself was quite proud of the fact that all the four constants that Planck had in his in this Planck units are in this equation. Nowadays, of course, we just call this thing A over 4 pi, where A is the area of the horizon. And indeed, Bekenstein, the student of Wheeler, indeed basically had this result, but not with all the pre-coefficients. So this is sort of where kind of the field kind of had to start thinking, because if this is indeed a true fact, can we actually understand what this entropy represents? And indeed, it turns out that the dynamics of a black hole, just by thinking about precisely the black hole mergers, which people were doing already at the time, they indeed had already discovered things that sort of hint at sort of an interpretation of this sort. So take a particle, it goes into a black hole. It turns out that it's actually possible to throw a particle into a black hole that reduces the mass of the black hole, surprisingly. If a black hole rotates and you throw in a counter rotating particle, this is called the Penrose process, by which you basically can extract energy from a black hole. But when people looked at this thing more closely, even though you can extract mass and energy from the black hole, you cannot extract entropy from the black hole. Turns out that any black hole, any process involving a black hole always increases its horizon. That in those days was already called the second law of black hole thermodynamics. The first law of black hole thermodynamics is the equation I have here, that indeed if you change the mass of the black hole, it indeed is associated with a change in the area. And if we now take this identification of temperature and entropy sort of as being a property of a black hole, it turns out that this equation and that equation kind of look very alike, and they basically should be kind of analogous. At least that was sort of the idea. But we moved on from this, actually. We went farther. The physics that leads to this equation is really sort of thinking about how black holes merge. The physics of this equation is to think about thermodynamics. You do what Boltzmann started doing, of thinking about thermodynamics as particles moving, or systems sort of doing the thing that thermodynamics tells them to do. So my brother, and Sibaji mentioned Eric already, he probably sort of made sort of the courageous jump of saying, hey, let's reverse the logic of all of this, rather than saying that this is an analogy. And there were other people like Jacobson that had done these things before. There's a whole field that's called ADS-CFT, where basically these equations indeed are equivalent. But suppose that we really turn the logic around. Then indeed, it's true that there are forces in nature that you can kind of think about as being the consequence of thermodynamics. And basically the question that Eric was asking is that, hey, if that's the case, and if we take the analogy seriously, could we potentially explain gravity as an origin, as having a thermodynamic origin? The way he implemented the idea was sort of in a way that sort of generated the discussion, and many details have to be filled in. And there are examples sort of in other contexts where we can make these things more precise. But this is one of the questions that we're still thinking about. Is there another way of thinking about gravity where it kind of emerges indeed from properties of sort of material properties of something that underlies it? One of the jokes that Eric made actually in his paper maybe even was that at the time when Newton wrote down the equations for gravity, of course, Newton thought that he was doing fundamental physics and he was thinking about how gravity works, and Newton's law works really well. Of course, there was a rival of Newton, Hooke, who indeed is known for Hooke's law. And of course, there was a bit of tension there. So it would kind of be a sort of a bit of an ironic thing if it turns out that Hooke's law is actually the fundamental law, and that gravity is a consequence of Hooke's law. I'm sort of voting for that one. Okay, since I talk about voting, so Andy, how am I doing with time? So we have 15 more minutes. Or, okay, good. Let's see, how am I doing? Okay, we still have a ways to go, so let me try to sort of go quickly here. So now I'm going to talk about the information paradox. I'll be quick here because I'll explain what's happening here. So Hawking indeed made the point that if you think about what black holes can do, it might actually be difficult to actually reconcile all the things that we consider as deep principles of physics. Unitarity is basically that you can predict the future, or that quantum information is preserved. Causality, you cannot go faster than the speed of light. This is an example basically of how we think about causality. If you do a computation, you want to basically know what the next qubits look like given your previous qubits. This is a bad computation where you basically forget about all kinds of stuff over here, and you introduce arbitrary new things over there, and you get an answer that is not correlated with the thing you put in. And basically, it turns out that for black holes, we're going to have a problem of just keep doing good calculations without violating other principles. I'm going to have a vote on this slide. So suppose you take a black hole, you throw a book into it or a whole library. Then according to basically what Hawking has done, calculated, basically Hawking showed that stuff can escape from a black hole. And if you think about it more carefully, basically a black hole burns. Basically it emits radiation, and everything, if you wait long enough and you put the black hole indeed in sort of vacuum, then the black hole will lose all its mass and it will send out everything in terms of radiation. So in some sense, whatever I threw into the black hole, actually from the point of view of the outside, burned up before it reached the horizon. Okay. Nonetheless, if I'm the book and I'm reading that book and I fall into the black hole, the book will just fall into the black hole. So which of the three things are going to happen? I throw a book into a black hole. Does it fall through the horizon? Does it burn up and become Hawking radiation? Or can both be true? So let's have a quick vote. Who says A? I say A. Who says B? I say B. Who says C? I may say C. Although I said A and B, but I'm not sure if I say A, if I say C. I have to explain. Okay, let's go with C. Okay, so C actually runs into a problem, which is called the no cloning theorem. Because if the book falls into the black hole, it's in the black hole, so it's in a state. If it also at the same time is outside of the black hole, then there should be a copy of the black hole, of the book that's outside. Now, okay, it could be the no Xerox theorem. Basically, if you have a Xerox machine that can copy a state, and normally if you copy something, you make another copy. But in quantum mechanics, that's a problem. If I make a copy of this thing, I get that state. But now if I take the sum of those two states, which I can do in quantum mechanics, and I make a copy in this way, I'm producing that thing, and this thing is not a copy of this thing plus another copy. So indeed, this is quantum mechanics tells you these things cannot happen at the same time. So it's not C for this reason. So let's see if we can sort of unwiggle our problem a little bit, or at least wiggle our way out of this problem. So one way of wiggling our way out of this problem would be still to do something slightly sort of dramatic. So here's the book that goes in. Here's the thing that should come out eventually. And perhaps what happens is that somehow this book changes its mind and comes back in time, basically, because time goes up and goes out again. Doesn't sound that great. But anyway, it kind of, you could argue that this thing perhaps is, if I unwind this wiggle here, is sort of equivalent to just the book coming out. So maybe this meant that the book indeed comes out. In some way of thinking about it, if you look at Hawking's calculation, he created actually a Hawking, we call it a Hawking pair. He created an entangled state over here at this moment. And this thing went in, and somehow there was something that happened here between the ingoing particle of the Hawking radiation together with this thing that sort of went into the black hole. So let's think about this a little bit more. And indeed, quantum mechanics can do these things. There's a thing that we call teleportation, quantum teleportation. Now you have to read this thing from left to right. Previously, time was going up. Now time goes horizontal. So just twist your neck and time goes up again. But anyway, so the Hawking pair that I was talking about is sort of here replaced by a thing we call an EPR pair. So here's this thing that sort of Einstein would definitely have called spooky actions at a distance. You make an EPR pair, you send it to Alice over here, one of them, the other one to Bob over there. This is, say, the book, or it's a quantum state of a photon. But anyway, Alice here is, by the way, sits near the singularity of the black hole. And she has a book that arrives. And then actually, there might be a bit of an issue here, but let's assume that they can have a bit of communication sort of earlier in time. Basically, it turns out that if Alice is doing an appropriate measurement on her partner of the APR pair with that state, then Bob can basically recreate that state. Even though Bob might be far away from Alice. So this is called teleportation. And by now people have done this thing over miles, or this maybe even longer. So people can actually transport photons. They cannot transport this quantum state of a book, but if they can do a quantum state of a book, this indeed would be an analog of teleportation, essentially. So that's part of the ideas, perhaps, is that one can actually perhaps get this book out of the black hole by teleporting. I talked about the Wheeler wormhole. We've created Wheeler wormholes in the lab. Actually, we have not, but in paper, there have been papers that have been published where people kind of describe the creation of a wormhole in the lab. And then I'm just being a little bit sarcastic here. Basically, they've done teleportation indeed on simple quantum computers, indeed with the same kind of scenario, but you could imagine doing teleportation through a wormhole. Because indeed across a wormhole there is indeed entanglement. But the idea, at least, that you can sort of communicate between the two sites, that for sure is correct. Whether or not it actually resolves anything about black holes is not entirely clear. Still, I'm racing a little bit for time. Can I take 3 extra minutes at the end? 10 more minutes? Good. 10 more minutes from now or from the hour? Okay, so I'm going to quickly sort of go towards the chaos and towards cosmology. I'll skip this slide mostly. So this is my advisor at Hoofd. Indeed, at the time when I was a graduate student, he was already doing all this stuff. He was talking about sort of things inside of black holes, and he had sort of basically already a lot of the story that we've been developing since. What he was doing, he was basically saying, hey, if a particle is close to the horizon of a black hole and I send another particle in, it will actually have a consequence for it. It will slightly shift it. Now, the problem with a slight shift is that most of the time you will not see it. But if you happen to be a particle that was hoping to get out of a black hole by just sitting barely outside of the horizon of the black hole, at that point you have to be extremely nervous. Because you could say, hey, let's look at my future. My future looks bright. I can actually make it out over here. But now it could be that there's another particle that goes in. That particle is the butterfly. And that butterfly slightly shifts you by just a tiny little amount. and your future will look drastically different. So this is actually an effect that we call the butterfly effect. Basically, if you have a tiny difference at a given moment in time, it can have an exponentially large difference in the future. And indeed, mathematically, indeed, if you think about a chaotic system, that's exactly how these things sort of trajectories diverge. It's called the Lyapunov effect or Lyapunov exponent. And we've used this in the last sort of 8-9 years as a way of thinking about quantum mechanical models of black holes. I'm not going to talk much about sort of the mathematics behind this, but we have quantum systems that basically have the same butterfly effect, and that indeed are a quantum system that one can sort of study as in the same way as you can sort of think about the time evolution of a quantum computer, except that this quantum computer at least has sort of an interaction where every bit can sort of start talking with every other bit, which means that if I make a very small change of one bit in the quantum computer, then basically my whole computation blows up. At least indeed it has this chaotic effect of what we call sensitive dependence on initial conditions. Indeed, it precisely also has this property that we call scrambling, where the thing can basically thermalize very quickly and become random very quickly. So the last 6 minutes, I'll talk about cosmology basically because of this question about black hole information has been around for a while. And the question is, what are the new things we want to think about? It turns out that most of the models of black holes that people have devised, and they are actually maybe not quite as realistic as we'd like them to be. The places where quantum mechanics applies, at least, are actually theoretical laboratories where the cosmological constant has been introduced, but actually initially with the wrong sign. This is called anti-de Sitter space. It turns out that for most practical or these real-world applications, the cosmological constant has to be positive. So in my last 5.5 minutes, I'll talk about basically the same ideas, but now in the context of cosmology. I talked about the horizon problem, and the horizon problem is indeed the question that something over there looks the same as over there. And the way people sort of solve that problem is by thinking about space as something that exponentially expanded very quickly, very early in the universe. Because basically, if that's the case, then our universe was much smaller in the past, and therefore things could have communicated with each other in the past. Personally, I don't believe in inflation. And I can tell you, basically, it's because this is the picture of inflation, where the universe was this tiny, and after a certain amount of time, it was much bigger. And actually, the number of boxes that you have to draw here would be, people talk about 60 e-foldings, they 10 to the 30 boxes or something like that. So this has a much bigger volume, and I find it very difficult to do a quantum computation that looks like this, where all the information that's in that cube was actually contained in that cube. I don't know how to do that. So basically, in my mind, there's a problem indeed with quantum information in cosmology. Again, unitarity, causality, and in this case, sort of the maximal amount of quantum information. Let me briefly talk about sort of the ideas of black hole thermodynamics, but now applied to our universe. This is you in our current universe. Here are all the galaxies. Fast forward many billion years, many trillions of years from now, the universe is currently expanding. Everything moves away from us. Basically, what it means that all the stuff here is actually falling in a direction, and the direction it's falling into is actually far away from us. Everything goes towards a thing that the cosmological horizon. The cosmological horizon is the place in our universe that if you're sitting there, because currently, because of dark energy, our universe is accelerating and it's expanding. It means that there's a place at the universe over there that's moving with the speed of light from us. So that's my horizon, and I cannot communicate with it. Okay? And it turns out that that horizon is actually the thing that attracts everything, because the universe is expanding and everything goes towards the horizon. Now, why is it doing that? The reason why it's doing that, this is, by the way, why I reduce time, because this button is not working. Here we go. So it's expanding because actually Hawking himself did a calculation with Gibbons, where he has indeed showed that the horizon of the universe also has entropy. It's the biggest elephant in the room. Its entropy is much bigger than everything else, 10 to the 120. So if everything sort of gets absorbed by the horizon, it's again because of the effect that basically anthropic forces, or just the time evolution of the universe, attracts things to the horizon of our universe. And personally, if I think about dark energy, I don't think about it as being one number. I think about it as being, if you plug it in, it's 10 to the 120. So 10 to the 120 qubits are sitting somewhere in our universe, and that represents the horizon. So where is that entropy hiding? What is dark energy made of? We're trying to figure that out. Let's go here. And actually, the model that in my mind is actually still the same model that I mentioned before, the Sastek-Yekitaev model, is actually a very good way of thinking about it. It turns out, why did I do this? Oh, here we go. I need to have this one first. It turns out that the Sitter universe is actually special. If you think about the entropy contained in the horizon of our universe, it's the area of the event of the cosmological horizon. It turns out that if I put mass in a cosmological universe, and you look at the back reaction of the mass, it reduces the total area of the horizon. So the area gets reduced, which means that the entropy of the universe gets reduced. I like this effect a lot. It means basically that the universe with maximal entropy, with maximal randomness, is an empty universe. If I start putting stuff into it, I'm making it more special, basically. I'm subtracting information from it. And indeed, the mathematical model that I've actually started studying in the last few years is still the same model that people have used for black holes, but I'm putting it into a place where actually the entropy is maximal. And it turns out that this model indeed has a place where the entropy is maximal. So I now have my little toy cosmology on my notebook. And I'm playing around with it, and I want to do one test, and that's my last half minute, where I'm going to do a test with my quantum cosmology, okay? First, I want to know if things make sense. Here's one thing that actually happens in cosmology. So I talked about black holes as horizons where you cannot sort of go through. Again, the same is sort of true in the cosmological horizon. This is, again, our universe. This in the future with an horizon. This is the Penrose diagram of that thing, meaning that this is the spatial slice, this is space, that's time. This little panicky figure sits here, the horizon sits there. And it turns out that if this world line of that person can communicate only with this region of space. And here's a picture of an expanding universe that explains that. Here's sort of a two-sided version of this whole thing, because indeed it turns out that there's another side to the cosmological horizon. There's a sphere, which is big. We're sitting, say, at the North Pole of it. If I want to talk to the person at the South Pole, that person sits at the other side of the horizon. Because basically this point here is moving away with the speed of light from that point there. And indeed, if I send a signal from here to the other side, it cannot reach the other side. So all of this part here is not communicable from that side. I talked about the shock waves, or at least the things that if I send in things in a space-time, it actually moves things around. And it turns out that basically in cosmology, it is actually possible to communicate between here and the person all the way at the other side of the universe. Even though we're separated by a horizon, it turns out that if I send in a particle, then precisely the shifts that Hoft was talking about here work the other way around. And it turns out there's going to be a gap, and I can actually talk to the person on the other side. So this is my plan for a computation that I want to do. If you have any ideas of how to help me with this, talk to me. And this would show me that I have a model of a cosmology. Let me end just with one of my other heroes in theoretical physics, Eugene Wigner, who was at Princeton, in sort of my birth year, I think 1960, actually before that. So he wrote a paper called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And he talks about many aspects of it, and he understood sort of this pretty deeply. I've been talking about all kinds of conceptual questions that we have, and our mathematical theory that underlies it actually has many equations. And many of those things work remarkably well. But for reasons that we don't fully understand yet, whether or not it's our own imagination that we think that these things work, or is it really true that nature follows laws of mathematics? But anyway, let me just end with this quote. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we can neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research and that it will extend, for better or for worse, to our pleasure, even though perhaps also to our bafflement, to wide branches of learning. Thank you.